In this video, we're going to continue to look at vectors and motion. So far, we've looked at vectors in one dimension, and in one dimension, they're kind of limited. Basically, we have a positive direction or a negative direction. And even though that is helpful and that is telling, we don't live in a one-dimensional world. We live in a three-dimensional world. And so we're going to take it up a notch and look at things a little more complicated and move into a second dimension. And in order to do this, we need to be able to use and manipulate vectors. So just a quick review here. Vectors and scalars. All quantities that we talk about in physics here will either be a vector or a scalar. A vector has both magnitude and direction. Scalar is completely specified by only a magnitude or just some number. So examples of vector would be like displacement, velocity, acceleration. Scalar would be time, distance, speed, so on and so forth. When we write a vector and we use handwriting, we're going to put an arrow on top of the letter. So when we write something like a vector A, there's going to be an arrow on top. When it's printed, it'll be bold and have an arrow. When I handwrite, and you can do the same, mine will have an arrow, but it's only going to have one little piece of the tip. I'm not going to take the time to draw both pieces, so you can draw that type of arrow if you would like. Either way, doesn't matter. And when we're dealing with just the magnitude of a vector, that will typically be in italics. This as well will be used to describe or represent scalar quantities. We can say that two vectors are equal if they have the same magnitude and the same direction. So if we look at these four arrows here that represent vectors, and we'll use arrows to represent the vectors, we look at all of them have the same length. And because they have the same length, they have all the same magnitude. But that is only part of the piece. In order for these to be equivalent, they have to have the same direction or orientation. And so if you investigate these and look at their orientation with respect to the horizontal, all of them are at the same angle. And so another way to look at it, these are parallel vectors, so they're in the same direction. So vectors that are parallel and have the same length or the same magnitude are going to be equivalent. Because of this, we can move vectors around in a diagram. So just because this vector is right here, as long as we keep its orientation and keep its size the same, we can move it to a position down here. And we'll do that to help us to add these vectors together. And when adding vectors, we have to take their direction into account. In one-dimensional motion, we did that, but it was just positive or negative. Well, now it's going to be more than positive or negative. It could be in both the x and y direction. And so in order to add vectors, we have to take their direction into account. Their units have to be the same. So we have to add meters to meters, meters per second to meters per second. We cannot cross over units. And there's two different methods that we're going to look at. One is a geometric method, which is a good representation of how to add vectors, but isn't very effective, so we're not going to do it a ton to actually get a numerical answer, but we will do it to give a physical representation. And then there's algebraic methods, which we are going to do most often because it can give us a true exact answer. The resultant of the sum of two vectors is noted as such, in that we have some resulting vector r is equal to vector a plus vector b. Okay, now keep in mind, this addition does not mean we are just adding the magnitudes. Adding vectors is very different than adding scalars. Adding scalar quantities, we just add the two numbers together. In vectors, we can't just do that. We have to do more than that. Let's look at a geometric method first in adding vectors. And when we do this, we first have to choose a scale. Now, typically that means we're going to choose a scale in which we draw. Now, if we wanted to actually find numerical additions using this method, we would have to have a precise scale of, say, 1 centimeter on the paper represents 30 meters or whatever it may be. We're not going to do this too much. We're not going to use scale drawings to give us numbers. However, we are going to use representative drawings to give us an idea of direction and magnitude. And so we draw the vectors with appropriate length and the direction specified. So with this, let's just keep them relative in size and make them drawn in the correct direction. And then we draw the next vector with the same scale and appropriate length and direction specified. And we want to move the origin of that second vector such that it's located at the end of the first vector. And we'll take a look at a picture to make this make sense. Let's say we have this vector A right here. So we're drawing vector A. It's some length. And then we want to add vector B. Well, we're going to start at the tip of vector A and draw vector B. And so we draw A at the magnitude and direction specified, and then we draw B at the magnitude and direction specified from the tip of A. And this is called tip-to-tail method. And so we can see that the resultant is just going from the original starting point to the final point. And this is our resulting vector. This picture gives us the relative size of the vector, seeing that this arrow is bigger than both A and B. So we should see that the magnitude of R should be bigger than both A and B. And it also gives us an idea of the direction. It gives us an idea of what is this angle. Now, if we actually drew this to scale and measured out these arrows, we could just measure this arrow using our scale and find the actual magnitude by using a ruler. The issue with that method is it's limited on your ability to draw precisely, and your answers aren't quite as accurate. This is called the triangle method or the tip-to-tail method, and we are going to use this just for a graphical representation. One thing to mention about vectors, just like in adding scalars, there is a commutative property or commutative law of addition. So A plus B is equal to B plus A. And we can look at this graphically here. If we have vector A and then add vector B, we get this resulting vector R right here. Well, if we do that the other way around, take vector B and then add vector A, we still get the same resulting vector. Now remember, vectors, as long as we keep their orientation and magnitude consistent, we can move them around. So these two vectors in red are equivalent because they're the same orientation, they're parallel, and they're the same magnitude. You can also do this with any number of vectors. So say we have 4 vectors we want to add here. We just keep going tip to tail to tip to tail to tip to tail, and then our resulting vector will just go from the original starting point to the ending point, and that is our sum of all 4. Another note about vectors is a negative vector, and a negative vector is defined as the vector that gives a 0 when added to the original vector. So if we have some vector A, the negative of A is a vector such that when you add vector A and negative of vector A, you get 0. So what does this mean? It typically means that they are off by 180 degrees. So in other words, they are in opposite directions. They will have the same magnitude, just be in opposite directions. And so that way when they're added together, they cancel out and get 0. This is one-dimensional motion here. So we can use this idea of a negative vector to subtract vectors, because subtraction is really just the addition of the opposite. And so if we want to subtract vectors, say we have vector A and we want to subtract vector B, if we were to add vector A and B, here's vector A, if we were to add, B would be up here and we would get a resultant right there. But we want to subtract, so really we're adding the negative of B. So the negative of B is just 180 degrees. This is 180 degrees off, and the same magnitude in the other direction. So that gives us our resultant right here of vector A minus vector B. As well as adding and subtracting vectors, we can multiply and divide vectors by scalar quantities. We're not going to talk about multiplying and dividing vectors themselves yet. But if we're just multiplying by a scalar, the result of this operation is going to still be a vector. We're simply just multiplying the magnitude or dividing the magnitude by that scalar quantity. If the scalar is positive, the direction of the result does not change, it stays the same. If the scalar is negative, which we will rarely deal with this, then it's going to be opposite of the original direction or off by 180 degrees. The other method we're going to look at in adding vectors is an algebraic approach, and it is typically called the component method. Well, in order to talk about the component method, we need to understand what are components of vectors. And so if we take some vector A, whatever it may be, and so we have this vector A, and it has a magnitude and it has an angle with respect to the x-axis, some angle theta. Well, this vector can be broken up into components. If we can think about it as how big is this vector along the x-axis and how big is this vector along the y-axis. And so we have an x component we call a sub x and a y component we call a sub y. And we know that these relate using one of our trig functions here of tangent of theta. Tangent of this angle theta is going to equal the y component over the x component, because we can take this y component and move it over to this side and we form a right triangle. And so from that, all of our trig relationships are going to come into play. And so we just consider these components to be the projections of the vector on the x and y axis. From all of those trig functions, we have a few different formulas that will come about. In order to find the x component of a vector, we take the magnitude and multiply by cosine of theta. And to find the y component, we take the magnitude and multiply by sine of theta. And so if we took these two components and added those together as vectors, we would get the resultant vector, or our original vector that we had before we broke it into components. One extremely important thing to remember is that those formulas only work if and only if theta is measured with respect to the x-axis. So we must measure the angle from the x-axis. If it's not, then we can change our axis, and we'll talk about that in a moment. But the components can be positive or negative, and so they can be in the positive x direction or negative x direction, positive y direction, negative y direction, but the angle must be from the x-axis. And the components also have the same units as the original vector. A few final relationships between the components and the vector is that we can use Pythagorean's theorem to find the vector from its components by squaring the two components, adding them together, and taking the square root, which, like I said, is just Pythagorean theorem of finding the hypotenuse of a triangle. And we can find the angle of orientation by using arctangent of the y component over the x component. Now this is where trig's going to come in handy a little bit. When finding the angle, you still may have to find theta with respect to the positive x-axis. The value will only be correct if the angle lies in the first or fourth quadrant, and if it's in the second or third, we'll have to add 180. And we'll see some examples where this comes into play later. So like I mentioned earlier, sometimes it may be beneficial to rotate our origin or rotate our x and y axis so that we have an orientation that's not vertical and horizontal but off at an angle, so that way we can keep this angle in a convenient location. Basically, we need to choose axes that are perpendicular to each other and adjust the components accordingly. We use these components to add vectors algebraically. And to do that, we take all the x components, add those together, take all the y components, add those together, and then we can find the resultant of the x and y components by using Pythagorean theorem and our arctangent to find the theta. Let's take a look at an example. Let's say we have a hiker that starts a trip by walking 25 kilometers at 45 degrees south of east. Okay, now what does that mean, south of east? If we look at the cardinal directions superimposed on our Cartesian coordinate system, east lies on the positive x-axis. So this is east in this direction. This is south in the negative y direction. And so south of east means we're opening our angle south of east. And so this is our angle right here. So if we're moving 25 kilometers south of east, then our vector is going to look like this. And we'll say that that is 45 degrees and this is 25 kilometers. So that's our first vector. Well, then after that, let's say the hiker moves 40 kilometers in a direction 60 degrees north of east. So if we're looking north of east, here's our horizon. North would open up in this direction. So 40 kilometers at 60 degrees north of east. So this is 60 degrees, and this is 40 kilometers. And we want to find what is the resultant vector, or what is the total displacement of this hiker. And so we're looking for this red arrow right here. Let's go ahead and call this red arrow R as our resultant vector, and we'll call the first one A and the second one B. So to add these two vectors together, let's start with breaking the vectors up into their components. So let's find A sub x and A sub y. Now, from our formula, we know A sub x is going to be A times cosine of the angle. Now, this is where this is very important. Is our angle measured from the positive x-axis? And yes, it is, but it is below the x-axis. We are measuring 45 degrees below, so this is a negative 45. So that means our x component is going to be 25 times cosine of a negative 45 degrees. It is very important to make sure that when you plug this into your calculator that you are in degrees, not radians, because if you're in radians, you're going to get a much different answer. So you could write this as an exact answer, but I am fine with you writing it as a decimal, and let's keep around 3 sig figs and say this is 17.7 kilometers. And so that's the x component of our a vector. To find the y component of the a vector, we're going to use the a times sine of the theta. So this is 25 times sine of a negative 45, which gives us a negative 17.7 kilometers. And this should make sense. We're at a 45-degree angle, so we're moving the same in the x as we are in the y, and this is negative because we're moving south and east. So that's the negative y direction. So that is good. That's what we want. Now let's look at b. b of x is going to, and once again we have to check, are we measured from the x-axis, the positive x-axis, and our angle is actually above the x-axis. So we're good. So this is going to be 40 times cosine of 60. And b of y is going to be 40 times sine of 60. When we plug these into our calculator, we get 20 kilometers for the x component and about 34.6 kilometers for our y component. So we want to add these vectors together. So let's take the x components, add those together, and then take the y components and add those together. So when we add these two together, we get our x component of our resultant to be 37.7 kilometers, because that's 20 plus 17.7, and our y component to be 16.9 kilometers. Now, How do we find the resultant? Well, we find the resultant by taking these two numbers squared, adding them together, and taking the square root. And so that gives us about 41.3 kilometers. So this is the magnitude of our resultant. But how do we find the angle or our direction? Well, the angle theta is going to be the arctangent of the y over the x. So that's the arctangent of the 16.9 divided by 37.7. So once again, we got to make sure we are in degrees, not radians. And so we get an angle about 24.1 degrees. Now what is this? This is 24.1 degrees above the x-axis. And so if it's above the x-axis, we can just leave it that. Any degree is assumed to be above the x-axis. Or we could say north of east. And so this is both the magnitude and direction of our vector.